So first 1 minute and 20 seconds of draft science babble.
So I'm doing a response in sorts. I didn't watch the Dispar video, but I did see it, so I haven't checked his channel in quite a while. Now, he's still doing experiments, all right, where he's using rubber bands that are stretched in this form. So the rubber bands are put across, he's comparing how much, you swing something in and moves the rubber band some more distance. And so as I pointed out, as I did the math, which I'm not a big fan of, realistically.
Oh, so you're not a big fan of math? Well, that already was pretty obvious.
The fact is you can figure out that you can't do this measuring this way. You can't measure how much you push in because it isn't proportional to how much you're actually stretching the rubber bands. So let's say if he has the integrity to accept the truth that Pythagorean theory says so. It doesn't take that much work to figure this out. Okay, that this length is not proportional to that length, and that this hypotenuse rho is disproportional to that length. And so I'll do the numbers again, but let's see this. So if I did it in clear 1 unit of distance, okay, and then 2 units of distance, and then 3 units of distance, and then 4 units of distance this way, the numbers came out. So this was, let's just say this is 5 centimeters. Doesn't really matter what number we use. Okay, so you start off at 5.0. The 1 unit of distance. All right, you end up with 5.099. All right, so this is your 1 unit of distance. This is what 1 unit of distance, 1 mark equals 0.99 stretch in the rubber band. That's how much it does. And then 2 units of distance, you get this huge jump, okay, to 5.385. Obviously, almost, 4 times the 99. So it's a lot more than what it should be, which is twice. So this is 2 units, this is 1 unit, this is 0 units of distance. All right, so go line here. All right, and then 3, okay, your number gets, really big. Okay, so now we're going 8, okay, 3, 0. So obviously 8 units of distance, and then we did 3. So huge disproportion, gigantic. And then you end up with, for the fourth, 6.403. So now you're a whole, 14 more. So it's only 4 times the stretch, 4 times the distance, but you're at 14 times the stretch in the actual rubber band. You stretch the rubber band 14 times the distance.
All right, so a lot of things needs to be said, and I'm going to need your focus. Keep concentrated, because it's going to be a lot. When you have a rubber band stretched between 2 poles, let's say it's 5 centimeters here. The rubber band measures 5 centimeters, and then I let a pendulum swing against it with 1 unit of velocity, and let's say it then stretches backwards with 1 centimeter. So 1 unit of velocity, 1 centimeter of linear stretch. So it stretches in this way. That's 1 centimeter. And then when I let the pendulum swing with twice the velocity, as I have demonstrated with physical evidence, it stretches with twice the amount of linear distance, 2 centimeter. And then when I let the pendulum swing with 3 times the velocity, as I have demonstrated, it will be pulled back very close to 3 times as much linear stretch. Okay? So 1 unit of velocity gives us 1 unit of linear stretch. 2 units of velocity gives us twice the amount, or 2 units of linear stretch. 3 times the velocity gives us 3 times, or 3 units of linear stretch. Okay, but so now draft science says this is not the total amount of stretch. It's not linear. It's not 1 centimeter of stretch, 2 centimeters of stretch, 3 centimeters of stretch. This is linear. Draft science says no, total amount of rubber band stretch is not linear, it's non-linear. Because we have to take into consideration these lines. As we pull the rubber band backwards with 1 centimeter each time, these lengths grow non-linearly. So when we start with 5 centimeter, when we pull it back with 1 centimeter, the total distance here, if you measure these lines, I've measured it with my ruler, it becomes 5.4 centimeters. So from 5 to 5.4, that is an extra of 0.4 centimeters, right? When you then pull it backwards with 2 centimeters, the total length of this and this becomes 6.4. So we start with 5, from 5 to 6.4, which is an extra of 1.4 centimeters. Now 1.4 centimeters is 3.5 times as much as 0.4 centimeters. So draft science says, oh, the total amount of stretch here only is 3.5 times as much stretch than this one. So even though you only pull it back with twice the amount of linear distance, the total stretch isn't twice as much, it's 3.5 times as much stretch. So it's 3.5 times as much energy. Oh, yeah. So it's close to 4, right? So kinetic energy says twice the amount of stretch, 4 times the energy. So draft science says, no, it's not twice the amount of stretch. It's 3.5 times the amount of stretch, or yeah, close to 4 times the amount of stretch. So 4 times the energy. Oh, that's how he justifies himself. And the same with when you pull it back with 3 times the amount of linear stretch. Kinetic energy says 3 times the stretch, 9 times the energy. Draft science says, no, it's not 3 times the stretch. When you actually measure this, we have 7.8 centimeters. So we start with 5 centimeters. Now we have 7.8, which is an extra 2.8, which is 7 times the amount. So 7 times the amount of stretch. 7 times more stretch than this one. So 7 times more energy. Yeah, closer to 9 times as much. So this is how he justifies the quadratic increase of energy. Even though it's a linear increase each time, 1 centimeter, 2 centimeters, 3 centimeters. So 1 unit of energy, 4 units of energy, 9 units of energy. Yeah, it's because the total amount of stretch isn't twice as much and 3 times as much. It's 3.5 times as much and 7 times as much. And it keeps growing closer to the quadratic increase than to a linear increase. Right? But so now here comes the debunking. So we have, when you pull back with 1 centimeter, right? When you pull a rubber band backwards with 1 centimeter, the total distance becomes 5.4, and we start with 5, so we have 0.4 centimeters of extra stretch. So this is now 1 unit of energy. So now, if we want to have twice the amount of energy, we have to add another 0.4 extra centimeters of stretch. So from 5 to 5.4, and if you want to add another 0.4, we would have to have a total amount of stretch of 5.8. So 2 units of energy would equal a total amount of stretch of 5.8. But then this linear distance wouldn't be 2 centimeters, it would be less. I've measured it, it would have to be 1.7. Right? The linear amount of distance would have to be 1.7 centimeters in order for this to be twice the amount of energy than this, according to draft science. Now I have, of course, that's wrong because I have proven it to be wrong, as I have demonstrated. When I let the pendulum collide with twice the velocity, it produced exactly twice the amount of linear stretch. So the same with 3 times the energy. So if this is 1 unit of energy, then 3 times the energy would have to be 3 times this. So if we start with 5 centimeters, 3 times the energy would have to produce an extra stretch of this times 3, so 1.2. So 6.2. The total amount of distance would have to be 6.2 instead of 7.8. So 6.2. This is 6.2, which means that the total amount of linear distance would not have to be 3 centimeters, but way less. It would actually have to be only 1.9. Instead of 3 centimeters of linear stretch, of linear distance, it would only have to be 1.9 centimeters in order for this to be actually 3 times the energy. But draft science says energy equals mass times velocity, right? Force equals double the force, double the motion, triple the force, triple the motion, right? So twice the amount of velocity, twice the amount of energy, 3 times the velocity, 3 times the energy, etc. So if this is 1 unit of energy, if this is 1 unit of velocity, right, then twice the velocity, or 2 units of energy, should produce a linear distance of 1.7 instead of 2. And then 3 times the velocity, or 3 units of energy, should produce a linear increase of distance of 1.9 centimeters instead of 3 centimeters. And that's absolutely not what happened in my experiment. I have demonstrated with my photo gate, the velocities can't be denied. 3 times the velocity produced a linear stretch of a distance very close to 3 times as much, not 1 times as much. There we go.
And to finish, a little bit of non-mathematical theory. Simple explanation: why the rubber band acts like a horizontal spring. The rubber band only cares about how far you pull it back, not about the triangle shape. When you pull the middle of the rubber band back, you feel a force trying to pull it forward again. That force is horizontal. That force is what stops the pendulum, so the rubber band feels the pull in the backwards direction, not along the sides. The triangle shape is just a side effect. It does not determine energy. When the rubber band forms a triangle, the 2 sides get longer. Yes, those side lengths grow in a curved, non-simple way, but the rubber band is not trying to fight that sideways length. It is trying to pull the middle back forward. That means the rubber band uses energy to pull horizontally. The sideways lengths are just geometry, not energy.